so it's up to you guys. Go ahead.
Did you upload the last video on YouTube?
Say again?
Did you upload the last video on YouTube?
Did I?
We did.
Okay.
I looked over.
Let me check. Let's see. Sometimes I put it up and then forget to unlock it. So last class is when? It's 5 days ago, so it would be the 13th. Yep, it's not there. Okay, I'll go ahead and upload it now. Wow, it's still here. I didn't delete it.
At least it ain't lost.
Yep, it's not lost. All right, so let's see. Doesn't seem to be working, this thing here. Nope. Let's hook up to this. There's no mic, there's no speaker coming out of it, so that's not gonna work.
We're gonna hear you overhead, huh?
Yeah. Alrighty.
You're pretty intimidating.
Okay, so what we'll do is we'll talk about the exam first. Okay, I know as much as we don't want to talk about it, it's kind of important to talk about it. There are no markings whatsoever on the exam, and that's why that you guys pass around because nobody can actually see the score of anyone else. I don't even know the score yet, so so don't worry about your educational record being visible to other people. So that's not one of the things that you have to be concerned about. I'm talking funny because of the gum surgery last Friday, and I was feeling pretty good, on the day of surgery, and the 2 days after, and then starting yesterday, starting to get sore. Okay. So today, I just have to drink Ensure. I probably cannot eat much today, so it's getting a little bit. It's getting a little bit uncomfortable. Let's just say. So there are several things that we have to do. We can talk about the exam. It's still being passed around. Who has it right now? Okay. So we'll probably I'll let you guys pass it around first, and before we talk about the exam, let's talk about your next homework assignment, the one that I'm assigning today. I kind of sound like Daffy Duck today because there's an appliance to protect the donor site on my palette. So that kind of helps, okay. But the other part where the grafting goes onto, that's hurting right now. All right, so your new homework assignment is called Flip, and it's not the same thing as the Flip program from last semester. It's a little bit different, not by much. And it's a tar file just as usual. Okay, so you want to download the tar file and untar it. So let me go ahead and do it so you can see what it looks like and what you have to do with this particular program. I think it downloads to downloads folder. Go, and we say tar zvf, and then the name is flip.tar.gz, and then we go here, and I give you the C program. You have to write the assembly code. All right, so this is the C program, and as you can see, this is a subroutine that is recursive. Okay, so we have to kind of figure out how to do things in a recursive way, and not use anything in dot data. Okay, that is kind of the most important part of this homework assignment. Is you're not supposed to use dot data at all, okay, and only use the stack. All right. How many people still remember what is an auto class local variable from your C class, cisp310? All variables by default are in the auto storage class unless you put a static in front of it. So when you look at line 4 and line 5, those two local variables are of the quote-unquote auto class, which means it is created on a per invocation basis. When you call a subroutine, the local variables get created. When the subroutine returns, the local variable disappears. Is that okay so far? Okay. So let's take a look at this code here, and we'll talk about the C code first, and then we'll talk about how to translate that into assembly. So in the C code, we have two local variables, ch and result. They are both local variables. We have the usual stuff. We're reading from the standard input file, and the result of the read operation is put into result because we have to examine result, for a few reasons. Okay. The first thing we do is to check whether we successfully read a single character or not. Because if we don't, we just say, okay, we didn't read anything and we're done. Okay, there's no recursion when we cannot read anymore from standard input. If we do successfully read one single character, then we go through this code here. Now this code doesn't do a whole lot. I mean, you can see that it has a conditional statement, which we already know how to implement. The first part, which is the then branch, is the easy one, okay? Whatever we read, if it is a space or the line feed character, which has an ASCII code of 10, we just assign result to ch, and then we get out of the conditional statement, which also means that there's no recursion in the then branch. The else branch, which means we did not read a space or a line feed character, then we call flip again. But when we call flip again, we'll store the result of flip, the return value of flip, into result here, and then we'll go ahead and write the character that we just read. In other words, we read a character, we recursively call flip, and when flip returns, we print or we write the character that we just read out. Okay? So if I give it like A, B, C, D, and then a space, what do you think would be the output? D, C, B, A. Yep, exactly. Okay? So this basically, that's why it has the name of flip, because it reverses the characters. But we'll stop the reversing as soon as it either hits the end of file, because then read will return the value of 0, or it hits something like a space or a line feed character. Those are all separators of words. So when it hits a separator of a word, it will stop and actually start to unwind from the recursion. The main program doesn't do a whole lot. It does do something. What it does is it has a while loop here, and in the while loop I use an assignment operation. This is not a mistake. This is not supposed to be a comparison. It is an assignment. So in the while loop, in the condition of the while loop, I would call flip, and then I take whatever flip returns and put it into result. And if it does return something that is non-zero, which means I'm not at the end of file, I will call write in order to write that one character out, and then go back and flip again. In other words, every time we call flip, it will only flip one word. And words are separated by either a space or a line feed character. Are we doing okay so far with a basic understanding of this code? Okay, so let's go ahead and try this. Okay, so we'll say gcc-g-o flip.c. So we're compiling the C program, and it does compile. Okay, it's a pretty fairly typical C program. You can probably get the C code to work in code blocks regardless of the operating system, because it only uses fairly standard stuff in C. So I think it will work across all platforms. And then you can run it. So I'm going to run it without GDB first. Okay. So I would say this is a funny little program. And then when I press the enter key, it will process that line, and will flip everything. Okay. Each word is flipped, but it doesn't flip the entire input. Okay. You can see how this is flipped, is flipped. And you can also see program is flipped, but the period is appearing at the wrong place because I did not interpret the period as a separator of words, which is okay. It's not a big deal, okay? Because otherwise I would have a really kind of huge, long disjunction to note to identify what is separating words. Okay. So are there any questions about the behavior of this program? Give me a word that can be spelled backwards.
Radar.
Hmm?
Radar.
Oh, radar. Okay, that's a good one. And radar, it says radar. Oh, that's a good one. How about another word that can spell backward, but then it spells another word?
Todd.
Okay. Okay, so that's what the program does. Okay, and a Dracula. For those of you who watch anime, you know what I'm talking about. Yeah. So that's kind of what this program does. And when you press Control D on the keyboard, it stops because that's the end of file. Okay, so that's the behavior of the C program. When you debug this program, I suggest that you do not debug it in the interactive mode because that makes it really hard to work with because GDB and the actual program will compete for standard input, and as a result, it becomes very difficult to work with your program. So what I would do is to prepare a test input file, and you can just put something that's simple, okay? So this is a simple test input file, okay? That's all, okay? Don't use anything that is too special. You can probably put in a few new lines just so that you can confirm that you can process new lines. This is the line, this is another line. That's it. Okay. So with that, the apostrophe and the exclamation point, those will be reversed as well because they are not a space nor a line feed character. Okay. So what you want to do is to do it like this. You can run the program all by itself, without GDB, and you say test.in, redirect from test.in to become the standard input file, redirect to test.out as the standard output file. So this way you have the answer, okay, of what it is supposed to do with that particular standard input file, okay, which makes it easier for you to test your own program, because if your program is not producing the same output using the same input as a test file, then it's not working. It is not consistent with the C code. Is that okay? All right. So now we can say, okay, what about in GDB? How do we do this in GDB? So in GDB, just say GDB flip, and when you run the program, you want to run it with the redirection, and that's okay. So let's set a breakpoint first. We'll put a breakpoint on, let's say, line 19. Okay. So we say break on line 19, and then we can run the program. But don't just run the program because we do have a test input set up already. So you want to redirect from test.in as the standard input file, and we can also redirect to test.out.1 as the output file. I'm not overwriting the other file because I just want to show you how you can maintain two output files, and the other one you can actually see it in another terminal as it is created, as it gets its content. All right. So now we have your flip running all the way up to line 19. In C, this is what you can do in C and C++. Is you can do a BT backtrace. Not backtrace. This is BT stands for, I think it's backtrace. No, BT. Nope, backtrace. So with backtrace, it shows you the level of recursion. So right here it shows you that main calls flip on line 25, flip calls flip on line 25, flip calls flip on line 25, and so on. And then right now we are on line 19. Okay. So it really is helpful because now you can actually see all the frames with each invocation. Now the other thing you can also do is to examine the local variables in each invocation, okay? Because remember what I said earlier in class, the local variables are allocated on a per invocation basis. So right now we have 1, 2, 3, 4, 5. We have 5 invocations of flip, okay? Which also means that we have 5 different sets of local variables. There are 5 CH, there are 5 results, and there's one set per invocation of flip. So what you can do at this point is to say, oh, I want to know what is CH for this particular invocation. Okay, so you can say print CH, and it tells me that it is a space. Okay, and that's why it stopped the recursion, because we have hit a separator of words, and that's why it's stopping the recursion. Is that okay so far? Okay. So in order to locate and say, okay, but I want to know what is the one before this. Okay. Then you can say frame, when you use the word frame, you have to specify which frame we are talking about. This is frame 0, 1, 2, 3, 4. So if you want to jump all the way to frame 4, which is the first invocation of flip, you can say frame 4, and this will get us all the way back to frame 4. Even though execution is still at frame 0, we can now examine all the local variables in frame 4, okay, which is a great help when you want to debug a program like this. Then you can say, print ch, but this ch belongs to the first invocation of flip, not the last invocation. What do you think should be ch at this point? Okay, let me show you the input file so you can actually take a look at that one. So we go to downloads. This is flip, and we take a look at test.in. This is the input. So what do you think would be in ch in the first frame, the first time we call flip? Capital T, uppercase T. So we'll go ahead and double check. Okay. So it's always helpful not just to print it out, but in your mind go through the exercise to figure out. Okay, I think it should be ch. Okay, and then you use the GDB to say, okay, it really is uppercase T. So this is really helpful because it does help you exercise your mind to try to understand what is going on here. And if your prediction is not consistent with the output of GDB, then you have to kind of figure out why is it not the same, okay? Because you have to debug your understanding of the concept, or maybe you input the wrong command in GDB. Maybe you're not looking at the first frame, okay? So this is how you can debug a program like this in GDB, and I strongly recommend that you run the C program a few times and go through GDB just to understand how it works before you try to translate that into assembly. Are there any questions about this? Nope. Okay. So I will single step, and it will go back to the previous invocation. So if I do a BT, now we only have 4 invocations of flip active at this point. Are there any questions about the word invocation? What is a invocation of a subroutine? Sorry, go ahead.
Are you asking us?
Yes, I am asking you.
It's call subroutine.
Mm-hmm.
Yes, so it's a way of putting it.
Okay.
Start knowing the protocols for a subset of instructions.
So there are 2 aspects to an invocation. The first aspect is time-wise, okay? When does an invocation start and when an invocation ends? An invocation starts with the call from the caller, and it ends with the return from the subroutine being called. Okay, so time-wise, that's one invocation. But there's another aspect to an invocation. It has to do with the local variables and the parameters of a subroutine. So those get created, quote unquote created, as soon as the subroutine is called, and they terminate when the subroutine is done. Okay. Okay. So let's take a look at this particular subroutine flip here. So right now we have 4 invocations. The first invocation is called by main. So on line 25 of main, we call flip. The second invocation is on line 15 of flip. It calls flip itself, and then on line 15 it calls flip itself, and then on line 15 it calls flip itself. And this is the current active invocation. This is where we are at this point. Okay. Are there any questions about this? No questions? Okay. If anyone feels comfortable with subroutines in general, but when it comes to recursion, it's not particularly comfortable or it looks kind of foreign, it has to do with a misunderstanding of how subroutines work. Okay. In other words, most people think, when they think about local variables, they think local variables are done on a per subroutine basis, as opposed to on a per invocation basis. That is the misunderstanding that stops people from understanding recursion. Because recursion is nothing special. I mean, the difference between flip calling A, calling B, calling C is not really any different from flip calling flip itself. It should not be different at all. So the confusion has to come from the misunderstanding of how local variables work. They're on a per invocation basis, not on a per subroutine basis. Did I talk about the U-Haul truck analogy? That's basically what it is. Okay, you have one single subroutine, which is one U-Haul truck, and invocations are basically rental contracts. Okay, so on the same truck you can have sublet and a sublet and a sublet, which also means you have multiple invocations of the same subroutine. Is that okay so far? Kind of? Okay. So with that out of the way, let's go back to the C code first. Okay. And then we want to figure out, okay, but how are we going to do something like this? I mean, we haven't really talked about local variables. No, we have not talked about local variables, but we have talked about certain things that you can use to kind of implement local variables. What do you think we have talked about that is usable in this case as local variables?
Stack. Stack.
The stack and its related instructions. So the push instruction and the pop instructions are going to be very useful in this case. Okay. Anything that you want to preserve on a per invocation basis, you probably want to put it on the stack. All right? And I'll give you some sample programs, not exactly the homework assignment itself, but it will be something that is related to the homework assignment. Okay? So are there any questions about the homework assignment before we move forward? I know that you guys have all done passing the exam, so we can talk about it, but I think this is more important. Okay, so we'll go ahead and finish this part first before we move back to the exam questions. Okay, so if this is okay, we'll go ahead and write another sample program, which doesn't really do a whole lot. Okay, I'll just call that sum.c. So sum doesn't do a whole lot. This one is going to take it's going to take a parameter, which I don't want to do. I can still use a global variable in this case, which is not really the best way of doing things, but since we haven't really talked about local variables, this is what I have to do. So I just called it sum. It takes no parameters, so we don't have to worry about parameters here. So we say if x, this one doesn't use any local variables. I can make it do it. So we'll say local variable n is here, and then we say if x is greater than 0, oops, return something here. Okay, there we go. All right, so the first question is, what if x is greater than 0? We'll go ahead and say if x is greater than 0, we store x in n. Okay, n is a local variable, and then we call sum. So we'll say, next is going to be n is n plus the recursive call of sum. Else we'll just say that n is 0. That's it, and return n. All right. So this is my recursive subroutine, and you can see it has some resemblance to your homework assignment. It has to return a value, okay, for one thing, and two, it has one single local variable in this case, whereas in your program it has two local variables, but the concept is still pretty much the same. And then in main, we'll do this easy stuff here. So we'll say in main, it has its own local variable. Maybe I won't use a local variable here. Okay, in main, I'll just say x starts with the value of 3, and then we call sum and store the result of sum back into x. Okay, that's all we're going to do. Are we doing okay so far with this? So what do you think is going to be in x when we get to line 22 when main is about to return? It's going to be an infinite loop, isn't it? So I have to remember to say x gets x minus 1 here. There we go. So x is going to be decreasing by 1 every time we do the recursion. So eventually it will be less than or equal to 0 and then stop. Okay. So when it does stop, n will be 0 and will return a 0. But when it comes back, to the previous one, n will still be 1, and then n will be 2. So we are actually adding 1, 2, and 3 together. So the sum should be 6. Okay, it's adding 0, 1, 2, 3, and the sum should be 6. All right. Are there any questions about this subroutine in C? No questions? Okay. So the first thing we'll do is to verify that really is the case. So we say gcc-g-o sum.c. This program does not have any output, so using GDB is the only way to see the result of this program. So we say GDB sum, we list program, put a breakpoint on line 23, run the program. Now we're on line 23. We say print x. X is exactly 6. Okay. So we kind of know how the C code works in this case. Now it's time to translate this into assembly. All right. So we'll go ahead and do a -o sum.c on one side and sum.s, the assembly code on the other side. This is the C code. I'm just using it as a reference. Oops. And this is the assembly code. Now in this particular case, I do have one global variable, and whenever I have a global variable, I have to use the .data section. Unlike local variables, global variables are statically allocated, which means all global variables start to exist before main is called, before your program gets get to the execution point, and it will continue to exist until you say exit. Okay, I'm ready to go. So that's why global variables are in the .data section. But in your program, you don't need it. You don't need the .data section because there are no global variables in your program. But X is the only one in the .data section. You can see that n is not stored in the .data section because n is a local variable, and local variables are not statically allocated, which also means if sum is not getting called at all, there won't be any storage allocated for local variable n. Are there any questions so far about the differences between a global variable and a local variable like n? No questions? Okay. So now I switch back to .text and the usual stuff, export underscore start, and then I can define the subroutine sum at this point. Okay. So if I define the subroutine sum at this point, then I say, I have a local variable n here, and local variable n is supposed to be allocated on a per invocation basis. So at the entry point of a subroutine, which is sum in this case, I should allocate for local variable n. Okay, let's go ahead and do it. Well, somebody already mentioned that it should be on the stack, right? So how do we allocate some space on the stack for a 32-bit integer? Sorry? Not .int. .int is statically allocating something. This is not going to be static. This is going to be at runtime. So whenever we get to this instruction, it will allocate just 4 bytes. And then later on, we'll have to deallocate those 4 bytes.
We subtract 4 bytes from
Exactly. So we say subtract long, and the number of bytes in this case, which is 4, from ESP. That is going to allocate exactly 4 bytes on the stack. Okay. It's almost the same thing as a push instruction, a push L, push long instruction, except in this case, I don't even bother to copy 4 bytes onto the stack because I don't know what those 4 bytes are supposed to be. I'm just allocating it. Are there any questions about what I just said? That this is almost like a push instruction, except I don't even bother to copy 4 bytes onto the stack. Yep.
Would this be quicker than pushing 4 bytes of 0?
Absolutely, absolutely. Because when you push 4 bytes, then you will have to do this anyway, right? You still have to adjust the stack pointer. But on top of that, you'll be copying 4 bytes either from a register, from an immediate operand, or from a memory operand onto the stack. The stack is in memory, so a push instruction always is costly because you are going to write to memory locations. This is super fast because all we're doing is to change a single register and decrease it by 4. This is a single clock instruction. I mean, it's like, it's done. Whereas the other one, you have to deal with memory. So it can cause all kinds of stuff happening, like the cache is outdated, write to memory and all kinds of stuff like that. So this one is way faster. And we can do this because we are only allocating, this is corresponding to line 5, we're just allocating the space for local variable n. We are not actually writing to it yet. Okay, I don't know what to put into n at this point. Okay. All right. So the way I do things is, well, let's just do it this way for now. Okay, the next instruction is going to be saying if x is less than or equal to 0, we go to the else branch, because that's how we structure, that's how we flatten a conditional statement. So we'll be comparing, this one is relatively easy because it is a global variable. So with a global variable, I mean, it's just x itself. We use a direct operand here, and we say jump if not greater than, and since it's an integer which is signed, so j n g would be the right conditional branch to use to the else branch. Okay, and I'm going to put the else branch right here, and also have jump to end if right away, and if it's going to be here. Okay, so you can see that when I write the code, I write the structure of the framework, and then I go back and kind of flesh out the content. Okay, so if I did not branch to else, it means x is actually greater than 0, which is now corresponding to line 8, 9, and 10 of the then branch of the conditional statement. N gets x. Now that seems to be a pretty easy thing to do, because it seems like we can just do a move L, x to n. It's not going to work for multiple reasons. First of all, if n did exist and can be addressed this way, it's going to be a memory operand. You can only have up to one memory operand at any particular time, so that's not going to work. And 2, we don't even have n in the assembly code. We reserved 4 bytes on the stack, and that's it. That is our n. Okay? So what are we going to do to copy the value of x to n? Well, since we know that we cannot have memory to memory operand, memory to memory move, I know that I have to put x into a register first. So let's go ahead and do that first. So we say move L x into a register, because we can do a lot more stuff with a register than we can do with a memory operand. Okay, so now EAX is effectively x. What do we do now? Tell me, what is the stack pointer pointing to right now? But ESP points to the last thing that we reserve, or the last thing that we push. What was the last thing that we reserved?
4 bytes for
The 4 bytes for
n.
for n. Yeah. Oh, so that means that ESP is pointing to n at this point. Now I'm going to stop and pause here, because this really is an important part of this assignment, okay, of this particular sample program. ESP is now pointing at n, because we just reserved it. Is that okay? I know? Okay. So we'll go ahead and do this, in case you need to review the video. The current time is 9:38, and obviously, recording this part is not going to help, because you have to watch the video up to this point. So you can write it down on your note here and say at 9:38, we talk about how to refer to a local variable that is previously reserved by a subtraction of the stack pointer. Okay, I can see a few people writing it down. That's good. All right. So at this point, we say, okay, since EAX is our global variable x at this point, we'll copy it to whatever the stack point is pointing at, because I just reserved that space for n at this point. So ESP is still pointing at that space that I just reserved for n. Okay. And now we can move on and say subtract 1 from x, subtract long 1 from x. That would be line 9 of the assembly code. And now we are on to line 10. Line 10 is a little bit kind of tricky. So we have to call sum first, because I can't really do the addition or the assignment until I have the result from sum. So I'm going to call sum first. Okay. There are no parameters to set up, nothing, so I just call sum. So when sum returns on line 13, The question now is, but we haven't talked about how to return a value from a subroutine. Well, we kind of have talked about that. Go ahead.
It's stored in EBX.
It's stored in EAX. It's in EAX just like with system surface number 3 and system surface number 4. The return value is in EAX. Okay, so in our own subroutine, we'll use the same standard. Okay, now in this particular case, since it is your code and it's not going to be interfacing with a C program, we can use any register that we want to. If you want to use EDX, so be it. Okay, you just have to be consistent. But I'm going to use EAX, as the return value. So assuming sum is going to store the return value into EAX, I just have to add EAX to n, which is what the stack pointer is supposed to be pointing at this point, and I'm done, right? So now this is the other part that you might want to write down. So starting from 938, we do have a few really, really key concepts that you have to kind of pay attention to, because in this case, I'm adding EAX, which is the return value of sum, to n. But where's n? N is still pointed to by ESP. Oh, hold on a second here. Okay, I'm not convinced because call is going to do something to the stack, right? Call is going to save the return address on the stack. So isn't ESP going to be different at this point? The answer is no, because the call instruction is counterbalanced by a return instruction of the subroutine that we are calling. Okay? Even though it is the same subroutine, it does have a return to balance off the call. So the return address that is pushed by the call instruction is going to be consumed by the matching return instruction of the subroutine being called. So the stack should remain balanced at this point. So ESP will still be pointing to n, and I just have to add the return value, which is stored in EAX, assumed to be in EAX, into n. And that concludes the then branch of the conditional statement. Now we only have the else branch to deal with. The else branch is a whole lot easier, because we just have to copy a 0 into the local variable n. And tell me again, where is my local variable n? The stack pointer is still pointing at it, right? So we're going to say move L, $0 immediate to whatever the stack pointer is pointing at. That's all we're going to do. So line 16 of the assembly code is matching line 14 of the C code. And after the end if, we can now say return n. Oh, we haven't talked about how to return a value yet. But remember what I said about the assumption? Which register is supposed to store the return value? EAX, okay? So in your code, you can use whatever register, but as a convention, GCC also makes use of EAX. So if you use EAX as a return value, that means your code is one step closer to be callable from a C program, from actual C code. Okay, so I'm going to use that standard and say, okay, my return value has to be EAX. And where is it now? Where is n right now at this point on line 18 of the assembly code? It's still pointed to by the stack pointer, right? So what I need to do now is to copy whatever the stack pointer point to, which is n, and copy that to the return value register, which I have chosen, EAX 4, and that's how I specify the return value. Okay, so I'm almost done here. Almost, not entirely. This would not be right. Why not? Because what does return do? Return is going to take whatever the stack pointer points to as the return address and go back to that location, right? What is the stack pointer pointing at this point? N. Do I have any use of n at this point? I'm basically after line 16 at this point. N has no use, right? So what is it doing on the stack? I don't need it anymore. How do we deallocate n on the stack? We know how to allocate it, so how do we reverse that? Adding 4 to the stack pointer. Okay, so we can add 4 to the stack pointer, And once again, this really does not, this doesn't consume much processing time because I'm not reading memory. I'm not even reading from the stack itself. I'm just saying, let's just add 4 to the stack pointer. Now, if you look at line 18 and line 19, you can replace those 2 lines with one single instruction. Which instruction would that be? Hop L EAX. Okay, it would do exactly the same thing, but I do want to separate it into 2 lines because line 18 corresponds to copying the result into the return value register, and line 19 is deallocating my local variable n. So each line has its own significance, even though they can be combined into one single instruction. Does everybody understand why I'm separating these 2 instructions instead of using one single pop L instruction, which will work in this case just the same? Okay. So now that I have, yep, go ahead.
I don't understand why.
Why?
Why you're separating them into 2 instead of just
Because
popping?
functionally they do different things. Because functionally, the first line, which is line 18, is
Okay.
copying n to the return value register.
Okay.
And then line 19 is going to deallocate my local variable n.
And pop does something different? What would
No,
pop do?
functionally they're the same.
Oh, okay.
But in terms of concepts, these 2 lines serve different purposes. But if I roll them into one single instruction, then it's hard to look at one single instruction and say it's actually doing 2 things.
Oh,
Okay? It
okay.
has 2 roles to that one single instruction. Whereas right now, one instruction has 1 role and the other instruction has a separate role.
Gotcha.
Okay. All right. So that's it. That's my sum subroutine. And we can now deal with main. Well, since we don't really have main in an assembly language program, we say underscore start. Underscore start is going to say move L3 to X because that's matching line 21 of the C code. And then we say let's call sum. When sum returns, what am I supposed to put back into X? The return value of sum, where is it? EAX. So move L EAX to X, and that's the entire program in assembly. So the last part is just to do the exit code, the usual stuff. EAX and that's the assembly version of this same program on the other side. Yep.
Another question. So when you did the n equals n plus sum, when you did the
On which line? Sorry.
9.
On
or
line
10,
9 of
10 in the C program, what did you do it? Like you called the sum, but how did you add the sum to the register?
line 13. Line 13 is adding the sum, the result of sum to n, because ESP or the stack pointer is still pointing to the local variable n.
But is the sum already in ESP?
No, the sum is in. Say that again. Can you ask the question
So
again?
like, how are you adding n to the sum? Because like, is the sum in ESP, or is it?
The return value of sum is in EAX, and n itself is pointed to by the stack pointer. So when you look at line 13, it takes EAX, which is the return value of sum, and add it to whatever the stack pointer points to, and that would be our local variable n. So that's why line 13 of the assembly code, or I should say, that's why line 12 and line 13 combined is doing what line 10 in the C code is doing. Okay. All right. So let's go ahead and see if this works. Okay. So we'll go ahead and get out of the editor. Assemble dash G is that's O. Sum.O, sum.S. And then we say link sum.o, gdb sum. So, and then we'll put a breakpoint. Now, you guys can definitely put a breakpoint, wherever you want to. I would put a breakpoint on line 13 just to see whether the recursion is working when I come back from sum is EAX, the expected result. So I would put a breakpoint on line 13, that's 1, and I would put another breakpoint on line 25, okay, because that's also the other place where sum is returning. I want to examine EAX at that point. So run the program. Now we are at line 13, which is right after the call. This is after the first. This is after the last invocation of sum has returned. Okay, and what do you think should be in EAX at this point? Nope. Okay, so X started off with 3, 2, 1, and then when X hits 0, it stopped the recursion and comes back. This is the first time we come back. So it should have a value of 0. Okay, so we'll go ahead and print EAX. It does have a value of 0. Okay, what about what the stack pointer is pointing at? Nope, not 3. 3 is the, okay, n has a value of 3 in the first invocation of sum. This is the second last invocation. The last one is already done, where x equals to 0. So this is the second last invocation. What do you think should be in n? 1. Okay, well, I think it should be 1, but doesn't mean that it's going to be 1, so we'll find out. Okay, so we'll say print whatever the stack point is pointing at. Examine works better in this case, so we'll examine W, which is a 32-bit content, at wherever the stack pointer points to, and it is 1. Okay, because we are just returning from the last invocation. This is the second last invocation, and if we continue execution, it will go back to the second invocation of sum. So at this point, EAX should be 1 from the previous invocation, and ESP should be 2 at this point. Okay, so we'll say examine at wherever the stack pointer points to, and it is 2. Okay, so we continue execution. At this point, EAX should be 1 plus 2, which is 3, and ESP itself should also be pointing to a value of 3. So print EAX 3, and examine where ESP is pointing to. It is also 3. So if I continue right now, it will go back to the main program, quote unquote main program, and at that point EAX should have a value of 6. Okay, so we are now back on line 25, which is in the main program, and if I examine the value of registered EAX, it does have a value of 6. So I'm fairly confident this code in assembly is resembling what the C code is doing. All right, are there any questions? Okay, yes, go ahead.
You had 2 lines that you said if these 2 lines combined would be a pop L.
Yes.
Is there 2 lines in the program that would be a push?
I can show you those 2 lines. Sum.s. The 2 lines that will combine into pop L EAX is line 18 and line 19. Because it's copying the content of whatever the stack pointer points to into EAX and then deallocate those 4 bytes from the stack, which is basically what pop L does. There's one difference. So go ahead. Huh?
Is there a push?
The push is kind of done by line 6, but line 6 really doesn't care what I use to initialize those 4 bytes. So it's really just moving the stack pointer and not really do anything to what the stack pointer points to, because it is an uninitialized local variable. So all we really care is to reserve the bytes, but not so much what is in those 4 bytes.
Like line 10?
Sorry? Go ahead.
Would line 10 be either half of that?
Line 10. Line 10 is what again?
The other half of the push instruction.
Correct, because that's the first time we actually put something on the stack. Yep. Yep.
There be any issues if you moved the subroutine farther down in the program so that it starts with the start and then it has the very
There's no problem, because in assembly code you can reorder the things all day long. The only thing you don't want to do is to interleave, things like that would not be good. But if you move the entire block, if you move the entire block from line 5 to line 20 to after the last line of underscore start, that will work just fine. There's no need to define a label before you use it in assembly. But in C you do. In C you either have a prototype or you define the subroutine first. All right, are there any questions about this one? There's one last bit of information that you probably need to know, regarding the original assignment. So we'll go back to flip at this point, and flip has 2 variables instead of 1, right? We have a ch as character and a result. Okay, so the question now is, how do we deal with that? Okay, now that we have 2 things on the stack that we need to refer to from time to time. Okay, are there any questions, about what I'm referring to? Okay, because ESP only points to one thing, right? So if you have 2 things on the stack that you have reserved for local variables, what are you going to do? Because the stack pointer points to only one of them. What happens with the other one? What do you do to refer to the other one? That is the question. There are several ways to do it. There's the clumsy way to do it, and there's the not so clumsy way to do it, but it will use a cisp instruction as a result. Okay, or a cisp addressing mode as a result. Which one do you want? Do you want the one that uses simpler instructions, but it is more in terms of the number of instructions? Or do you want to use the one that is more complex in terms of addressing mode, but it will save you a few instructions?
Let's start with the simpler one and then work our way up to the more complex one.
Okay. So we'll go ahead and modify some, maybe, so that it has multiple variables. This one actually does not need multiple variables. That makes it harder to figure out how to do this. Okay, I'll do this. So let's just say that we have a variable called useless, and it is useless. It's completely pointless and useless. But we're going to use it somewhere, just so that we know so that we have to go through the exercise to actually refer to it. Is that okay? So we'll just go ahead and say I'm going to put useless here, and it's going to store the value of oh, this is what I'm going to do. Okay, so thank you. Okay, so I just changed the program a little bit here. So instead of using sum directly in the addition, I'm now storing the value of the return value of sum into useless, and then I use useless to add to n. Okay, so very slight change of the code, but it does make it necessary to reserve 4 more bytes for useless. Is that okay? Okay, but it will demonstrate what to do in assembly code to accommodate this rule change here. So I'm going to do a -o with sum.c on one side and sum.s on the other side. So now we can look at both the C code and the assembly code at the same time. Okay. So now we say, oh, we need 8 bytes. Now, you have to be careful because now that we are reserving 8 bytes, we also have to reclaim all 8 bytes at the same time at the end. If you don't want to mess around with the already existing instructions, then you want to say, okay, where's n and where's useless? So let me show you the stack at this point, in the subroutine. So ESP starts off, pointing to ESP originally points to the return address on line 6. Okay, before line 6 executes, the stack pointer points to the return address, which was put onto the stack by the call instruction. Okay, that's what return needs to use in order to do the return, right? So now I'm going to say, oh, you know what? We need to reserve 8 bytes instead of 4 because we have 2 variables that are local. So we're going to reserve 8 bytes here. Okay, so we have 4 bytes here, 4 more bytes here. So by reserving 8 bytes, that means ESP will be moved down by 8 bytes. Is that okay? Since most of the instructions of the subroutine is already assuming this is n, we better not change that, okay? Because otherwise I have to make massive changes to the program. So I'm going to say, oh, you know what? This is going to be useless. Is that okay so far? So the stack pointer points to the local variable n, but 4 bytes above that would be the local variable useless. All right? Okay, so now that we have that allocation, we go back to the assembly code and make all the necessary changes to make use of useless. So the way we make use of useless is to use useless. So this part has to be changed. On line 12, because I'm no longer storing the result of sum into, I'm not using it directly in the addition. I'm now storing it into useless first. Okay, so this would be a kind of an interesting exercise. In other words, how do I move EAX, which is the return value of sum, into useless? Okay, because this is not going to work. Because ESP points to n and not useless. Okay, so ideally speaking, this is kind of what we want to do, but we can't do it like this. The syntax of the assembly code does not let you do something like this. But this is sort of what we want to do. We want to say, oh, you know what? 4 bytes above where the stack pointer points to is the variable that I want to access, which is useless, right? So that's kind of what we want to do, but it won't let us do this. So let's talk about the, okay, which one did we agree to talk about first?
Actually, thinking about it now, we should probably just do the risk way and then do the sys way.
The risk way? Okay, let's do the risk way first. Okay, so to do the risk way, there are a few ways to do it. Okay, I will do it the clear way first. Okay, so the clear way to do it is to say, okay, let's make a copy of the stack pointer. The stack pointer is more or less a general purpose register, so whatever we can do with the other registers, we can do it with the stack pointer as well. So I'm just going to copy it to EBX because I'm already using EAX as a return value, so I'm using the next register EBX. And I would say, oh, you know what, EBX is close to what we want, but not quite. Okay, so we're going to say, let's just add 4 to EBX. Okay. In other words, if you look at the picture here, the first instruction, the instruction on line 13, is doing this. It's making EBX and ESP point to the same space, which is our n. The next instruction, which is adding 4 to EBX, line 14, is moving EBX so that it now points to useless. Are we doing okay so far with that? Okay. So at this point, I can say, oh, now that EBX is pointing to useless, we can finish the move instruction, which is moving EAX, the return value of sum, into whatever EBX points to, because EBX is now pointing to useless. Okay. So technically speaking, I don't have any use of EBX at this point, but the next instruction needs it, right? So assuming that we don't have EAX around anymore, the next instruction, which is line 12, is going to add a value on the stack to another value on the stack. I'm not reusing EAX even though I could. Okay, so what we need to do now is to move whatever EBX points to, which is useless, into EAX, and then add EAX, which is basically useless at this point, to n, which is what the stack pointer is pointing to. But you do have to remember to adjust the deallocation, because at the end of the subroutine, this is no longer a pop L EAX instruction, because we are not just deallocating 4 bytes, we are now deallocating 8 bytes. In other words, the first instruction on line 22 is copying n to become the return value of this invocation of sum. That's what line 22 is doing. Line 23 is now saying, oh, you know what? We are now ending this invocation. We have no use of n, and we have no use of useless anymore. Let's deallocate all 8 bytes at the same time. Why deallocate only 4 bytes at a time? We can deallocate all 8 bytes at the same time by adding 8 to ESP. So that's why in this case, it's not appropriate to combine the two instructions into one because they do have different roles. Okay, one specifies the return value, the other one deallocates the local variables. Okay. Are there any questions about the assembly code or the adjustments to the assembly code because of the second local variable useless?
This
Yep.
line 17, why did you do an add L instead of just a move?
Instead of,
A move.
because we are, okay, line 17 is implementing line 12, so we are adding.
Okay.
Actually, I should correct myself. Line 16 and 17 together is in assembly code is implementing line 12 of the C code. So that's why we're adding and not moving. Okay. All right. So let's double check and make sure this code still works, as expected. So we'll go ahead and reassemble. Just reuse the assemble command. Relink gdb sum. And I'll just put a breakpoint on line 29 in this case. I'm assuming the program is going to work fine. And it is still working fine. Okay. Are there any questions about this particular program? The one that makes use of a second local variable. Because that's kind of what you need to do with your own program. Okay. Any questions? Any questions? Okay. Now let's just take one last look at your own program, which is flip.c. Oops. Oh, that's not going to work. Okay, so let's take a last look of flip.c here. Okay, so we'll go through this line by line. Line 4 and line 5. Okay, we allocate on the stack. There's no need to allocate just 1 byte for CH. If you want to, you can allocate 4 bytes. Okay, so at least 1 byte for CH and exactly 4 bytes for result. So we'll go through line 6. Line 6 is pretty easy. You just do the system read operation and copy the return value, which is now EAX, into result. Okay, which is something that we have done in the other program already. Result, if result equals to 1, CH is somewhere else. So you do need to refer to the two local variables a little bit more often than the other program, but it's still, both variables are on the stack. Okay. Let's see, is there anything really tricky here? The only tricky part is on line 11, because on line 11, CH is a single character, it is only 8 bits, and result is 32-bit. Okay, so for that one to work, you have to clear out all 32 bits of result first, and then copy the byte over. Okay, just so that the rest of the 32-bit, the other 24-bit, is not garbage. Yeah. So other than that, it's not much. You actually don't have to clear out the most significant 24-bit, because the only reason we can be on line 11 is because line 7 is true. If line 7 is true, the most significant 24 bits, they all have to be zeros anyway. So there's no real need to reinitialize those 24 bits. So yeah, so this is, I would say my sample program that I did today is pretty closely resembling the homework assignment. Not in terms of functionality, it's not reading and writing, but in terms of the recursion and the use of local variable, it's kind of mirroring what we're doing here fairly well. Okay. Okay, that was the RISC instruction. So I can now go back to talk about the cisp instruction, which is actually pretty tempting in this case. So I would copy sum.s to sum2.s, which is so you can see the comparison of these two code, the 2 lines of code, or 2 versions of the code. Okay, so in the second case, it's this part here. Let me go display both of them. So I'll display both the original C code and the assembly code, so that this way we can kind of cross-reference between them. So the question here is on line 11, how do we make use of useless? Okay, the current way of making use of useless is on line 13, we copy the stack pointer to EBX, and then on line 14, we adjust EBX so that it points to useless, and then on line 15, we can finally get to useless, okay? The cisp addressing mode method is very tempting because what it does is to say, let's see here. So I basically can combine all of this to, this is what we call the based addressing mode. The base addressing mode, on line 13, so line 13, the second operand is basically saying it's almost like just the indirect operand, except in this case you can specify a constant to add to the register before it dereferences. So the 4 in front of the parentheses on line 13 is the offset. In other words, we are saying, yeah, the ESP is almost there, but we want to have a little offset of 4 bytes from where ESP points to.
So it's kind of like when you wanted to add 4 to ESP4, but you couldn't do that.
But it doesn't have any lasting effect on ESP itself.
Right.
So it's really just computing the sum of ESP plus 4, and then use the sum as the address to dereference, which is exactly what we wanted, right? So given that, we can also use the same addressing mode in the next instruction. Yep, so we can do this, you can use the same instruction in the next one. So basically, a 0 offset from ESP is n, an offset of 4 from ESP is useless. So it is very tempting because it really is easy to use. It's called the based addressing mode. And in this case, in the base addressing mode, like on line 13, the second operand, ESP is called the base register. It's just a name. I mean, it's no, there's no particular value to it. Okay. Are there any questions about the comparison of the previous approach, which is kind of cumbersome, and this approach, which is kind of clean? Yep.
If there's a push instruction, can't we just keep pushing things on the stack and then popping things as we need them?
Yep.
Can't we just keep pushing things there?
You can keep pushing stuff on the stack, but when you're done with one invocation of a subroutine, you better clean up the stack, because when you get to the return instruction, ESP needs to go all the way back to point to the return address. Yes, but you can keep pushing stuff if you want to. It's just that whatever you push, you have to pop. You have to balance the stack whenever you're done with the stuff that you push. But with additional push instructions, this is going to get a little dicey because every push instruction will move the stack pointer. So if you do any additional push instructions, your ESP will be pointing down here at that point. So the offset to get to n and useless will now be different. So you have to kind of mentally, on a piece of paper, keep track of how far ESP is away from n and useless, which is actually a very good lead-in to using the frame pointer, which is what we'll talk about next time. But this is the basic structure. This is the basic idea of how to use the stack for local variables. Any other questions about the assembly version of the C code? Is this kind of, how many people got exposed to the concept of recursion in a previous class? Okay, most of you. And is this kind of helping you understand how recursion is really done? Kind of? Okay. Yeah, it was the same thing for me. I didn't have C++ class at the time. They were teaching it in Pascal, but Pascal has recursion too. We have local variables just the same. But in the Pascal class, it was really difficult to understand what is happening with recursion. Because when you read the program, you think there's only one set of local variables. So when the subroutine call itself, what is happening to the local variable? I mean, how does it keep track of all of these different versions of the same local variable? It's until I took assembly language programming and understand how the stack is being used, Then it just suddenly dawned on me and go like, oh, so this is how recursion works, because each invocation has its own set of local variables. So if you imagine the stack here, so every time we call sum in this case, it has its own version of a return address, its own use list, its own n. Okay, the next time I do the call again, it will set up more stuff on the stack. Okay, so any questions? Yeah, we only got 5 minutes left, so we not quite enough time to talk about the homework assignment. I mean, the exam. Is there any particular exam question that you want me to go over in 5 minutes? My own copy here. And by the way, what do you think of the exam? Was it kind of hard, easy, time consuming? Which one was the most time consuming one? Number 2? Okay, so number 2 is to decompile the program. Okay, so it's a decompiling of a program, and
Question 1 should be pretty quick. It's just fix any problems with it.
sorry?
Question number 1 should be pretty quick to do. Just
Yeah, question number 1, I kind of eased it up a little bit. I did not put in too much tricky stuff. So most of the stuff that we went over in the practice test, if you just kind of look for most of those things, it's already answering most of the questions. Question 2 is decompiling. So it depends on how quickly you can recognize the structure of a program. And I did not really make it, very too tricky. And someone asked me, can I use a break instruction or can I use a break statement? And I said, okay, fine, use a break statement if you need to. Which is not very structured. Okay, a break statement is not a very structured way to write the program. And then the last question, I was hoping it would be the easiest one. Okay, no. Well, now that you have the test back, you can actually type in that code and actually run it and figure out what it does. The last one, in question number 3, it is kind of like the reverse of Treasure 2. Okay, because I think it resembles Treasure 2 more than Treasure 1. So what you need to do first is to lay out the memory content and find out how the bytes are arranged in memory in the .data section, and then figure out the most tricky part is probably the 2 move L in parentheses EAX to EAX, okay, because they're in sequence, right? It says one after the other one, and that has to do with L1 is a 32-bit. L1 is the label of 32 bits that actually has another address of L1 plus 4. And guess what is at L1 plus 4? Another 32 bits, which turn out to be the address, and that would be L1 minus 10. So that's why we can have 2 indirect dereferencing, and in order to get to the location of L1 minus 10, and then at that point, the rest are a little bit easier. All right. Okay, so any questions about the homework assignment? Because I do want you guys to kind of focus on the homework assignment first. I did make the question for today, but I didn't have time to give you guys the pop quiz because we spent the entire class talking about the homework assignment. Sorry?
Pop quiz?
The-
Not push quiz?
Oh yeah, push quiz and versus pop quiz.
Extra credit right there.
That would be a pop Q instruction, right?
Allocate my answer.
Well, it's still online, even though it doesn't count for any grade. I want you guys to answer it just to make sure that you understand the instructions, how it works, okay? So you want to go online, it's on Moodle right now, I can show you. We quite have enough time to talk about it. It is here, okay, so it is online now. I made a time release, so it is released at this point. So don't turn it in. It's not going to count for any grade, but I do want you to work on it just so that you know what the answer is supposed to be. Okay, so we have 2 push W instructions and 1 single pop L instruction. And I want to know what is the content or the value of EBX at the label check here. Okay. So it is still important, okay? Even though we didn't do it in class, it is still important. And hopefully next time we have time to do another pop quiz. All right. Well, it's on Moodle, so you don't have to copy it. It really is on Moodle. All right. So we're going to end today's class, and we are 30 seconds short, but I think Mr. Fox will appreciate it.
It's 30 seconds of his life.
Oh, 30 seconds is 30 seconds, right?
Yeah, it is.
That's a lot of milliseconds.
That's true. 800 clock speed, right?
Yep.